Now let's focus on IPTables implementation. IPTables is the Internet Protocol software or user interface to net kernel which allows your Linux system to implement a fully featured firewall, which means stateful as well as stateless firewall. It operates primarily at layer 3 and 4 of the OSI model, and again allows you to filter traffic into and out of your system. Let's label this section IPTables, and it's primarily a firewall for Linux. However, IPTables is an interface to NetFilter, which is loaded by the kernel during startup of the system. Because it's a firewall, it operates primarily at layers 3 and 4 of the OSI model. And by primarily, we mean for the most part, since a firewall can be configured to operate at various levels, including layer 2 when filtering based on MAC addresses, or layers higher than 4, such as 5 through 7, when using application-based plugins. IPTables is modular, which means in and of itself it's loaded or called by the kernel as NetFilter, as modules, and also supports advanced functionality such as proxying and access to layers higher than 4 using modules that you can download from the internet. So it's a full-featured firewall. In addition to all these features, IPTables provides network address translation support. So it provides network address translation, or NAT, support, which means you can turn your Linux box into a router similar to a home base Linksys or SMC or a D-Link or similar device, or even for an office such as a Cisco base or compatible or comparable router. So you can use one IP address connected to the internet and share it with all of your internal hosts. It provides forward and reverse NAT translation, which means outbound and inbound based NAT translation based on ports, distinct IP addresses, and so on. So IPTables is fully featured. Again, it's an interface to NetFilter, which means IPTables is a user-spaced application or user-based application that we interact with to gain access to the firewall that's loaded by the kernel when the system starts. It is enabled by default, and one way you can check is to execute grep config netfilter from boot config for the version of the kernel that you're running. The config file that's located in boot contains all of the options that were enabled or disabled for the current build of the kernel. If we navigate to boot and ls, you'll see that the version of the config file is 261853 for this system. So if we grep config_netfilter from boot config 2618, etc., nothing's returned because it's represented in uppercase, as are all of the options. But if we case-insensitively search, you'll see different options that pertain to NetFilter, with the most basic option, config_netfilter, set to yes. Let's update our documentation to reflect the case-insensitive search for NetFilter options that are configured in the version of the kernel that's operating on our system. So again, config_netfilter equals y tells us that NetFilter support is enabled with the current version of the kernel. Now there are different modules that are supported, including network address translation, classification, queuing, the ability for NetFilter to log traffic that you instruct it to log, and many other such features that are indicated as modular for the most part, which means they can be loaded when the kernel loads NetFilter by calling the appropriate module. Here we see a match MAC. This is access to layer 2 of the OSI model. It provides NetFilter the ability to, or with the ability to filter traffic in and outbound based on layer 2 MAC addresses, which you can reveal on your system by executing ifconfig and by extracting the hardware address associated with the network interface that you'd like to filter on. So IPTables allows you to filter based on this layer 2 address. So by primarily, when we mentioned before, primarily layers 3 and 4, we should also note that you do have access to other layers. IPTables can also access other layers, i.e. 2 and 5 through 7, with modules, such as the connection match for the MAC address that is configured to be modular for this particular system. So we see match _MAC in our output, which is set to modular. So enough of the dry theory. We know that IPTables is supported because NetFilter was compiled with the kernel. Let's identify the primary RPM package. RPM query all grep I case insensitive as usual, IPTables. This will search the RPM database for IPTables and return any applicable packages, which includes the primary IPTables package for version 4 of the IP protocol and the secondary IP version 6 IPTables package. In the next section, we'll look at IPTables6. In this section, we focus on IPTables version 4, since version 4 is the predominant protocol. RPM queryless IPTables reveals all of what's included with the IPTables package. It isn't too much, by the way. We see that in the init.d directory, there's an IPTables entry, which means IPTables can be started as a daemon, or initialize when the system is booted if rules are defined for IPTables. The default configuration that we've elected to set up on this system has no IPTable rules in place, which you'll see momentarily when we execute IPTables with the -L option to examine the contents of the default table. That's the filter table. We do see beneath lib IPTables various modules, but before we get to the modules, there is a sysconfig entry located beneath etc, and in a separate shell. Let's just attempt to interact with the file. We can look at it as a non-root user. It contains options that are to be loaded by IPTables when it starts. Again, there's an initd entry, which means when the system boots, IPTables will start as a service. Here are any modules that are loaded. IP connection track with NetBIOS name session support, and if there are other modules that are to be loaded, you can indicate as such by space separating the desired modules. Whether or not modules are to be unloaded when the service is restarted, that's IPTables, or stopped. And by unloading the modules, we release some of the system's resources, namely memory. Whether or not IPTables is to save its configuration when it's stopped, it's set to no by default, but if set to yes, will cause IPTables to write the rules to this file. And that is the file we've interrogated, etc sysconfig IPTables. Whether or not to save current firewall rules on restart. Again, it's written to the same file if the value is set to yes. So there's a save on restart as well as save on stop directive. It's advised that you set both of these to yes in the event that you intend to use IPTables heavily on your system, so that you don't run the risk of losing rules that may have taken you a considerable amount of time to write. Whether or not to save counters, depending on your environment and the requirements therein, you may need to determine, or you may need to save the counters associated to have it incremented whenever IPTables is restarted, so you have a full or aggregate view of traffic that passes through the various IPTables rules. If you're an ISP, for example, and IPTables guards some of your customer systems, perhaps, depending on interface, you may want to save the counters so that you have a total packet count, a means for quantifying traffic flowing through to and from a given client system. So setting the save counter to yes will ensure that whenever the system or IPTables is restarted, the counters will resume where it left off. So if IPTables, when stopped, for example, made it to, let's say, 600,000 packets, then when you resume, you'll be at 600,001 packets and onwards. And there are other directives that are defined in the file. So again, this file tells us, the IPTables-config file that is, tells us the configuration information IPTables is to read when it starts. If there's just a plain IPTables file, it will contain the rules that IPTables is to process when it starts or restarts. Again, nothing's saved, so it doesn't exist. But keep that in mind as you work with IPTables, that you'll need to send the rules or save the rules into etc sysconfig IPTables. Let's just note that. Save rules in etc sysconfig IPTables so that when IPTables is restarted, the rules will be applied. Or update etc sysconfig IPTables-config to save the rules automatically. And we'll look at both momentarily. Now, returning to the output again, there are various modules that are included by default with the IPTables package, including rules for classification of packages, destination net, connection marking, net maps, mirroring, masquerading. All of the features that IPTables can provide, or most of the features we should say, are included via the modules. TCP support, UDP support, time to live, type of service, you name it. It's implemented by a module, and there are many other modules you can download online. The primary binary is located in SBIN, and it's called SBIN, or it's called IPTables in SBIN. There are two other useful binaries that we can use to work with the access control lists. So this file is the primary ACL modifier utility, whereas restore restores the rules to the currently running instance of IPTables, restores rules to current IPTables instance, whereas IPTables saves rules to stdout by default, or to a file if you use output redirections. After you've created your rules or your access control entries, which constitute your access control lists, you should save the rules to a file, a text file, preferably etc sysconfig IPTables, or to some file that's accessible that you can use to restore the rules when you're ready to return or resume functionality. Now, with all that said, let's just discuss the tables, the default tables that you cannot delete that are included with IPTables. IPTables includes 3 default tables. As its name implies, IPTables, it manages rules or access control entries in tables, and it ships with 3 tables that you cannot remove. So it includes 3 default tables which you cannot remove. They include the NAT table, where rules are stored for network address translation, the mangle table, where packet mangling takes place, any source NAT, destination NATs, or any sorts of mangling that need to occur will happen in the mangle table. The filter table, which is the default table, includes inbound and outbound rules. Filters inbound or inbound and outbound traffic. It includes inbound and outbound rules, but it filters inbound, outbound traffic based on common criteria including TCP, UDP, ICMP, and other packet attributes. These are your 3 tables. When concerned with network address translation, you'll make use of the NAT table. You'll include rules in the NAT table. When concerned with handling packets, massaging, changing, making changes to fields within packets, you'll use the mangle table. And when simply filtering in and outbound traffic, you'll include rules in the filter table. That's where we'll spend our time, focusing on the filter table. Again, just like we've mentioned before with respect to OpenSSH and OpenPGP, for more information about filtering with IP tables, take a look at Linux CBT Firewall Edition, where we spend roughly a day's worth of time focusing on simply IP tables as it applies to IP version 4. So these are your three tables. The way you interact with these tables is to use the IPTables command. So, usage, IPTables-L, upper L that is, by default lists the contents of the default table, which is the filter table. Let's clear screen and give that a try, and you'll see it lists the contents of the default table. Each table contains chains, and this is a spillover or carryover from the old IP chains environment, which is the prior dominant firewall used within Linux environments. So within a table, there are chains, and chains are like access control lists, which includes access control entries. So each chain, such as the input chain, includes access control entries. In our case, we have no access control entries in any of the chains. Let's just note that each table includes chains which include access control entries, or ACEs. So looking at the default filter table, we see no access control entries, but there are some characteristics that should pop out at you, or some attributes that should pop out at you, including the fields that you typically specify when defining rules, such as a given target, a protocol we should filter on, any options as they apply to the protocol that you're focusing in on, the source of the traffic, if applicable, and the destination of the traffic as it applies. Now, when looking at the input chain, this perspective means, if you take the perspective of the system where IP tables is in effect, it means traffic inbound to a process running on the local system. So let's just note the filter table includes three chains. One, input, and this applies to traffic destined to a service that our system is bound to or listening to, whether TCP, UDP, ICMP, or any supported protocol. We also saw the forward chain. Let's just show you that again. The forward chain is used to influence or control routing. Applies to traffic being routed through the system. So if our system's a router, we want to include rules within the forward chain, which will determine which packets are accepted and forwarded into and out of the machine, which usually gets routed to a local area network system such as another host or a remote host, or a remote host located, let's say, on a remote network. So the forward chain applies to traffic being routed through the system, which is seldom used unless your system's a router. And last but not least, within the filter table there is the output chain, which applies as its name applies, or as its name implies, applies to traffic sourced from our system heading outbound. Outbound could be a process that our system is listening to, or it could simply be a remote process, meaning a process on a system on our intranet or on a system on the internet. So within the filter table, we have 3 chains. We primarily work with the input and output chains. These are the important ones because we're not routing. Our system's not set up as a router. But once you know how to write rules for input or output, you can write rules for forward and for the other chains in the other tables. So with that said, let's write some rules restricting traffic heading into the input chain of our remote system. So tasks 1, filter inbound traffic to remote RH5 system using, of course, IP tables. Well, first let's set up a connection to our remote host, Linux IPTables4. We'll open a new session. In fact, we appear to have an instance open over here, and we'll make use of it instead of opening a new session. So let's clear this window, return to serve 4, where we have apparently a session going. Let's go ahead and try to reestablish that connection. And once there's root, which we need to be in order to run IP tables, we'll execute IP tables list. We will see that there are no rules applied, and we'll apply a rule to restrict connectivity to SSH. And we know from netstat.ntl that SSH is a port that the remote system's listening to, but it's also listening to other ports, including FTP, HTTP, as well as IMAP and POP3, IMAP secure, and POP3 secure. So with that said, what if we wanted to, as our first task, to restrict access only to SSH? So we'll filter inbound traffic to remote RH5 system to SSH. Using the IPTables command and the input chain of the filter table, we'll execute IPTables, append the A option to input chain, followed by the rule that's of interest. Now, there are various things we can specify in our rule, including a target, a protocol, any options, which are optional, source, and destination. You need to make the determination as to what you need to restrict or how you need to filter traffic inbound. If it's simply to restrict all inbound traffic to TCP port 22, for example, then you don't need to indicate a source IP address or even a destination IP address. You simply need to indicate a destination port. You can do so after indicating the protocol type. So protocol type is TCP and the destination port is 22. You must also indicate a jump target using the J option as one of drop, deny, accept, and optionally log. Usually we'll indicate drop, which means IPTables will simply drop the connection without sending a response, a courteous response, to the person attempting or the process or user attempting to connect to the service. Whereas with the deny option, a courteous response will be sent to the person attempting to initiate the connection, indicating that connectivity is not permitted. Whereas accept means the traffic will be accepted. But if you notice, with each chain, the policy is set to accept. Each chain or each access control list has a default policy, no differently than a firewall. The policy is accept, but can be changed using the lowercase p option to be deny, which means you'll need to have access control entries that permit traffic. The default behavior is to accept traffic, leaving it up to us to explicitly deny traffic. So again, IPTables append to the input chain, and since there are no rules, this rule will be appended as the first rule in the chain. The protocol is TCP. The destination port is 22, and because it's going to apply to the input chain, it means any traffic sourced from any remote system to our local TCP port 22. But we did indeed say we wanted to accept 22 and drop everything else. So this indeed should become an accept rule, and then the next rule should be a drop rule. Let's take a look at that again. Now you'll see that there's a new rule in place, or one rule in place. The target, the jump target is accept. Protocol TCP with no particular options. These are options that pertain to attributes of the TCP protocol in this particular instance, or if it were UDP or ICMP of those protocols. Any source, any destination with a destination port of SSH will be accepted. So this means we should follow up with one more rule to drop all traffic. IPTables append, which will make it rule number 2, input. This time we don't need to specify a protocol. We simply want to drop all traffic, regardless of protocol. You could indicate TCP, UDP, ICMP independently if you'd like on the input chain, or just indicate drop. Now when we list, we see that there's a drop target for all protocols instead of a specific protocol, any source, any destination. Now since IPTables rules are top-down like most firewalls, in particular Cisco firewalls, the first rule, which is an accept, matches and doesn't kick us off the system because indeed we're connected to TCP SSH or TCP port 22. But for all other traffic, we'll be denied. For example, we saw in the netstat NTL output that the remote system, Linux IPTables4, is listening to a number of other ports, including POP3. Let's try to connect to POP3 using Telnet from our local system. We'll Telnet to its IP address, IP version 4 address. Remember, what we're doing here applies only to IPv4, not IPv6. 199, port 110 as the POP3 port, and it's failing. IPTables list. The second rule is dropping the connectivity. Now if we had set up a logging option for this rule, we would see the drops being logged, and we'd have proof of it if we instructed IPTables to log to a file. But we cannot connect to 110. How about attempting to connect to any of the other ports, such as 21 or 80 or 143? 21 is FTP, doesn't work. 80 is HTTP and it doesn't work, and 143 is IMAP, it too doesn't work. However, when we Telnet to 22, it picks up the phone. So right now, without turning off services on the remote system, that is Linux IPTables4, IPTables is functioning as a first line of defense from remote connections into the local system. Now you may be wondering, how about connectivity from the remote server, Linux IPTables4? Well, let's try it. We'll Telnet to localhost 22 or to 21, which is FTP. Notice that it fails because the input chain also applies to traffic source from the local system. A deny is a deny if no destination IP address applies. In other words, if there isn't a specific IP address in the destination field, it applies to all IP addresses. It's the equivalent of saying triple colons for IPv6 or quad zeros for IP version 4. All traffic is denied. We can try all ports with the exception of the lone 22. We will not be able to gain access to the local system's SSH instance. Now for 22, it has to be listening to that loopback address in order to facilitate connectivity into port 22. It isn't listening to loopback adapter, but it is listening to 192.168.75, 199.22. Now we'll go ahead and kill this. Let's netstat NTL grep 22, and we see that SSH is listening to all IPv6 addresses on port 22 as well as IPv4. So this is working as expected. We're filtering inbound traffic into the host using the input chain. Conversely, if you apply a rule to the output chain, it would prevent certain traffic from leaving the system. So for example, locally on Linux IPTables4, if we wanted to deny outbound TCP port 22 access, we could make that a possibility. So filter outbound traffic to any remote SSH port using the following. IPTables append to the output chain of the filter table protocol TCP destination port 22 drop. The This will match on outbound, meaning any access or any attempt to access port 22 either locally or remotely will be denied. We need to be root to apply this particular rule. We'll Control-Shift-V, echo the exit status, it's clean, and now when we IPTables upper L, we see that locally we have an outbound rule to drop SSH outbound access, which means if we attempt to telnet, let's say to 192.168.75.199.22, we're denied. And that's because of this output rule. Now how about flushing the chain altogether, removing the rules from the chain? IPTables upper F does that for us. If you want to flush all rules, so flush all rules from output chain of the filter table, it's quite straightforward. Simply execute IPTables upper F, the name of the chain, which is output, and this flushes all of the rules in the chain. It zeroes out the chain. It's the equivalent of clearing an access list on a Cisco device. So let's flush it. This is also much easier than removing the rules one by one. Echo the exit status, it's clean, and now a rerun of IPTables lists reveals that the output chain has no rules with a default policy of accept, and now if we attempt to telnet to port 22 it works, and if we execute the escape sequence it kicks us out as expected, and we still have our session open on the remote system using SSH. So we've modified the input, the output. You can list chains, you can view the counters associated with the chain. You may also zero out the chains. For example, a list would resemble the following IPTables list with the V option. This reveals the packets in and out of the various chains where rules apply, and you can see number of packets that have matched a given rule. So we see 366 packets, not bytes, but packets, amounting to 25,896 bytes matching the SSH rule, whereas 72 packets or 6,263 bytes matching the drop rule. You can zero out the counters associated with any of your chains by using the Z option, followed by the name of the chain, such as input. And then re-execute the list V, and you see that the values were zeroed out. We're now down to 8 packets and 00 for the drop rule. IPTables also supports creating subchains. So for example, we know that within the filter table there are 3 chains, input, forward, and output. We can further segment either of or any of the chains into subchains by using the upper N option to create a new chain. So we'd use the upper N option followed by, let's say, the input chain to create a new chain, such as a grouped chain for NetBIOS access or a grouped chain for web server access. It provides a way for us to group and organize rules. That's the upper N option. Now about saving our rules. We did mention that we can save independently of the options that are set in etc sysconfig IPTables-config. So another task will be to save rules. Save rules to file, then flush rules, and then our task after that will be to reinstate the rules. IPTables save dumps to standard out, which means if we use output redirection followed by the name of a file such as IPTables.rules.1, this will send the output to IPTables.rules.1, which we can use to reinstate the rules at a later point. So again, IPTables save dumps the rules to standard out. However, IPTables save with output redirection sends the rules into a file named IPTables.rules.1 or .rules.1, which means if we were to IPTables flush, so it's IPTables list, and then determine what to flush, we'll flush the input chain. So IPTables flush input, which removes all of the rules. We can reinstate the rules at any point by using IPTables restore. which is our fifth task. Reinstate flushed rules, using, of course, IPTables4 followed by the file name IPTables.rules.1. This will reinstate the rules for us and behaves similarly to what the IPTables init service does when instructed to save the rules on restarts and or on stops. So let's reinstate the rules. Echo the exit status, which tells us it ran cleanly, and now an IPTables list shows again that the two rules are in place, which means only SSH traffic will be permitted inbound to the remote system. Now again, as mentioned, IPTables is a wide world. There are many options, many things we can do to apply rules in or outbound. You can interact with any of the tables. We told you that the default table is indeed the filter table, but there are other tables such as the NAT table, as well as, and that's table NAT, that is, the NAT table, which has 3 chains itself for pre-routing, meaning what to do with the packets prior to routing, post-routing, and output. And then there's also, as mentioned, the Mangle table, which allows us to make changes to packets before routing, on input, while being forwarded, on output, as well as post-routing. IPTables is powerful. Many commercial firewalls and open source firewalls are based exclusively on this powerful engine, and we did mention that it's included as a module. So if you ls mod, it dumps the different modules that are loaded by the kernel when the kernel is up and running. If you search, you'll see IPTable modules, including NAT, Mangle, NAT, connection tracking, the filter table. So each table is represented, one for IPTables itself, and any other options that you may wish to enable that's included with the IPTables package. So this is an IPv4 firewall. We've looked at filtering inbound, brief outbound, saving our rules, restoring them, and we did mention that we would make changes to the default startup environment in etc sysconfig IPTables config. We'll set save on stop to yes, as well as save on restart to yes, such that in either case the rules will be saved to an appropriate file. And again, if we psef grepi IPTables case insensitive, we see nothing returns. However, when the system boots, indeed, it executes etc initd IPTables as a service. You may execute status, and it dumps the current rules. You may restart, which causes it to save, and also causes it to reload the appropriate modules that are currently running. And also, as a consequence of restarting, it saves the rules to etc sysconfig IPTables. A cat of etc sysconfig IPTables reveals as such. Here are the rules. If we stop the service, it'll do the same. Stopping unloads the modules, but it doesn't prevent us from listing the default filter table or any of the tables. So now the default is in place, which means our rules are saved, which means if we IPTables start again, or restart, and then rerun IPTables list, we should see that the rules are in place. 2 simple rules, albeit, but nonetheless it illustrates the point that with Red Hat Enterprise 5's etc sysconfig IPTables-config file, we can easily instruct it to save the rules for us whenever we restart or stop IPTables. Now we're going to be looking at IPTables version 6 next to show you how it applies to the version 6 of Internet Protocol, since we do have an IPv6 address bound to the system. And then we'll move on to other items.